So we will start with the presentation of Mr. Pedro Tradecete about the free Banach lattices. So I think you can start.
I'm muted, sorry. Yeah.
Okay.
So thank you, Amal, for the introduction. Thank you for to the organizing committee for the invitation and for arranging this wonderful conference. And in particular, I want to thank Amin for his, I'm sure his energy and enthusiasm have been important for the success of this conference. So I'm going to talk about Banach lattices, free Banach lattices, and maybe I should start apologizing because in this lecture there will be no direct connections to math economies or finance, or at least I'm not aware of any of these connections. So it's a more functional, analytic oriented talk. So anyhow, this is based on several works in progress with Niels Lausen, Timur Eukberg, Mitchell Taylor, and Vladimir Tradecete. And I want to discuss today some recent progress we have made on this notion of free Banach lattices. So, let me just start by recalling you, of course, in this community, that shouldn't be necessary, but let me recall what is a Banach lattice. Well, essentially, we have a Banach space, which is also a vector lattice, and we impose some compatibility conditions between these two structures, right? So we have this thing here, which is the relation between the lattice structure and the norm, which we require to be, we require the norm to be monotone with respect to the absolute value. Okay, so the kind of questions I want to focus today is a relation, the relation between these two structures, right? The Banach space structure and the Banach lattice or vector lattice structure. And by that, what I'm going to do is, if you like this category language, we are going to construct a functor which goes from the category of Banach spaces and bounded linear operators between them to the category or the subcategory of Banach lattices. And so the objects, the Banach spaces will go to Banach lattices, and bounded linear operators will go to the morphisms in the subcategory, which are the linear lattice homomorphisms. Okay, so throughout all this talk, when I say lattice homomorphism, I always mean a linear lattice homomorphism. That is an operator which commutes with all the, of course, with the linear structure and the lattice structure, and in particular, we know this is always a continuous map. Okay, so maybe before I go into details and speak about the free Banach lattice, let me mention a couple of examples that somehow motivate the kind of correspondence I want to look at. So we are all very familiar with this, with the correspondence between compact Hausdorff spaces and the corresponding spaces of continuous functions on there, right? So if I start with K, the compact Hausdorff space, I can associate to it this space of continuous functions on it with the supreme norm, and this is a Banach space. And it is well known that if you start with two compact spaces, then of course, if they are homeomorphic, the corresponding Banach spaces, C of K and C of L, say, will be linearly isometric. So you can identify them as the same Banach space. And the Banach-Stone theorem tells you the converse, right? That if you start with two Banach spaces of continuous functions, which happen to be isometric, then linearly isometric, then the compact spaces underlying have to be homeomorphic, right? And so this is this is the kind of mapping or the kind of functor I'm looking at, right? So this would go from the category of compact Hausdorff spaces, equipped with the continuous functions between them, into the space, into the category of Banach spaces, or maybe the subcategory of spaces of continuous functions. Similarly, one can consider for a metric space, there's the theory of free Lipschitz free Banach spaces, which again associates to a metric space, a Banach space, and Lipschitz maps on the metrics between metric spaces transform into bounded linear maps between the corresponding Banach spaces. So this is the source of examples, or the two examples that one could keep in mind as mainly as a motivation and to try to grasp what are the kind of questions one could address with the technology of free Banach lattices. Okay, so let me recall what the free Banach lattice generated by a Banach space is. So we start with a Banach space, call it E, and I'm going to define the free Banach lattice as well. The free Banach lattice generated by E is going to be, of course, a Banach lattice. I will call it FBL of E with square brackets. And it will be always equipped with a linear isometry from the original Banach space E, right, into the FBL of E. And the idea is that this linear isometry allows me to view or to consider the original Banach space E as sitting inside, as a subspace sitting inside of FBL of E, of the free Banach lattice. And it will do that in such a way that the elements of this subspace, of the image of this linear isometry, they behave as lattice-free generators of the free Banach lattice generated by E. Okay, so one way to express this, which is very convenient, is by using the following universal property. Okay, so one can use this as a definition for the free Banach lattice generated by a Banach space E. So we have this linear, maybe it's better if we just look at the diagram in the picture here. So you have this delta, which is just an isometry linear isometry between E and its image in FBL of E. And the property, the universal property we have is that whenever you take any Banach lattice X and any bounded linear operator T, right? So this is just bounded and linear. Then an operator T from the original Banach space E into the Banach lattice X, then I can always extend this linear operator to a lattice homomorphism between the free Banach lattice FBL of E and X, and this extension is unique. Okay, so this is another way of defining, this is the way one can use to define the free Banach lattice. And well, of course, because of our choice of the norm, we will make sure that the extension of this T hat, this lattice homomorphism extends without increasing the norm, right? This is property which is written here. Okay, so you can take this, as I said, as a definition. But first of all, one should make sure that such a creature exists. And well, this was done first by Ben de Pacter and Tony Wickstead, which were actually the first to consider free Banach lattices. They were considering the free Banach lattice generated by a set. So there was no extra structure. And one can see that their construction, which was of course based on the well-known theory of free vector lattices that was developed over the 60s and 70s of the 20th century, they were able to create a norm version of this, right? So they could make give a meaning to the free Banach lattice, or they could show the existence of the free Banach lattice generated by a set. And in the terminology we are using here, one can check that their construction can actually be seen as a particular case of the free Banach lattice generated by a Banach space. In that case, if you start with any set, if you take the Banach space little one over that set, then in our terminology, this recovers the free Banach lattice over the set A that was introduced by the Pachter and Wickstead. But okay, what we did is that is first show that this makes sense for any Banach space. So every Banach space has a free Banach lattice generated by E with no condition on the Banach space E. And this was done on a paper by Antonio Avilés, José Rodríguez from Murcia here in Spain, and myself. And actually what we proved was not only the existence of this Banach lattice, but also we could identify it as a certain space of functions. And what is more important, we could give a explicit expression of the norm, which I will comment on in a couple of slides. So as you see, this is all pretty recent. For the last few years, there have been several works in different directions related to this. I would like to mention maybe the work by Avilés and Rodríguez Avellán on the free Banach lattice generated by a lattice, right? So now you start with a lattice, not even a vector lattice, just a lattice structure and some set, and you can define the free Banach lattice generated by that in a very nice way, similar to the one we had for Banach space. And also one can consider certain versions of free Banach lattice under some convexity conditions. So for instance, one can consider the free P-convex Banach lattice or free Banach lattice with upper P estimates and things like that. And this was done pretty recently in a joint work with Hardon, Lawson, Taylor, and Tradecete. Okay, so as I said, let us have a look at, let us look at these spaces from a different point of view. Or let's see that we can actually view them as a certain space of functions living somewhere. So for that, as I said, you start with a Banach space E. So I'm going to look at the Banach space dual of it. I will call it E star. And I will look at the space of continuous functions on the unit wall of this dual space, which of course it's a weak star compact set. So I will consider weak star continuous functions. And I will require these functions to be positively homogeneous. I mean, I will only consider positively homogeneous functions, okay? By that I mean that every time I have a function and a positive scalar, you can take it out of the, right, for every positive lambda. This is positive homogeneity. And for any such function, one can define the following expression. So maybe I don't have much time to expand in order to justify this formula, but at least let me note here that if you're familiar to the theory of absolutely summing linear operators between Banach spaces, this is essentially the set of maps, nonlinear maps from the dual of a Banach space into the scalars that are one summing, right? So they map weakly summable sequences, which is these kind of expressions, into strongly summable sequences, right? Which is something like that. So maybe let's forget for a while about where this norm is coming from. Let us look at first, a particular case of functions one can consider the linear functions, right? So if I start with a vector x in my original Banach space E, then of course I can look at the evaluation function delta of x, which is of course a weak star continuous functions on E star, on the particularly this weak star continuous on the unit pool, and it's linear, right? So it's actually, in particular it is positively homogeneous, so this delta x belong to this space. And if I look at that space and I consider the lattice generated by the deltas, okay, so I take all possible deltas with x in my original Banach space, and I start making lattice combinations of them sitting inside the space of continuous functions on the unit pool. And I take the closure of all these linear combinations with respect to the norm I have just defined, then I get the free Banach lattice generated by E. Okay, so of course this requires a proof. This space with this norm, what I mean is that it satisfies the universal property of the previous slide. And of course, I didn't mention this, but the universal property essentially characterizes the space. So if you have two Banach lattices which satisfy the universal property, then one they have to be isomorphic, lattice isomorphic. Okay, so a couple of comments. One can check very easily that the mapping delta, defining here, going from the original Banach space E into the free Banach lattice generated by E, which maps every vector x to the corresponding delta of x, it is in fact a linear isometry when you consider it with respect to the norm given above. This is just, well, that's a simple observation. Also, I would like to note here that if you, in the expression of the norm here, the number of vectors you take in the sum, you force them to be n equal 1, right? So you just take combinations of vectors xi stars, which are on the unit pool. Then in particular, you get that this supremum, the supremum given the norm, is larger than the uniform norm, right? So this is larger than the sup of f of x star with x star in the unit pool of E star, right? So this allows me to view FBL of E, I mean, to consider this inclusion, the formal inclusion of the free Banach lattice generated by E, into the space of continuous functions on the unit pool as a continuous map with norm 1, right? So this is a linear and continuous map. Of course, the norms are different, right, between these two spaces, but you have this continuous inclusion. And in fact, one can show that the two spaces coincide. I mean, the space of continuous functions on the pool, or maybe the free Banach lattice generated by a Banach space E coincides with the space of continuous functions precisely when the dimension of the underlying Banach space is finite. Okay, in the case where you have finite dimensions, of course, looking at positively homogeneous functions on the ball is the same as looking at functions on the sphere. And in finite dimensions, there's no issues with continuity. So essentially, you have that for finite dimensions, the free Banach lattice generated by a finite dimensional Banach space is just the space of continuous functions on the unit sphere of the Banach space, but of course with a different norm. Actually, a norm which will be equivalent to the uniform norm, but whose equivalence constant will depend on the dimension. And as the dimension increases, this goes up. Okay. So one consequence of the universal property, which is very useful, is the following. If you start with an operator between Banach spaces, T, so a linear bounded operator between two Banach spaces, I can consider E inside of FBL of E by the mapping delta of E, and F, I can view it inside FBL of F, the free Banach lattice generated by F. And now if I look at the composition of T with delta of F, I'm having here a mapping between a Banach space E and a Banach lattice. And the universal property allows me to extend this to a map T tilde, which makes everything commutative. And this map T tilde is a lattice homomorphism, right? It's a lattice homomorphism. So this allows me to extend, to transform, if you want, a bounded linear operator between Banach spaces into a lattice homomorphism between the corresponding free Banach lattices. And in particular, it is very easy to check that if you start with an isomorphism between Banach spaces, then the corresponding extension or the corresponding lattice homomorphism will be actually a Banach lattice isomorphism, right? You just take T and the inverse and you play with them and you check that the extension, or if you want the tilde of the inverse, coincides with the inverse of the tilde and so on, and then you get this, okay? What we do not know at the moment is whether the converse of this holds. So if you have two Banach spaces whose corresponding free Banach lattice are lattice isomorphic, is it necessarily true that the Banach spaces, the underlying Banach spaces, are linearly isomorphic? And so we don't know the answer to this yet, but one can look at what is known in the literature in other or similar contexts, like Banach-Stone theorem, and one could try to adapt the proof. And I mean, you can do something. You can prove some facts about how lattice homomorphisms look like between free Banach lattices, right? If you remember, there's a classical fact that between spaces of continuous functions, every lattice homomorphism has to be a weighted composition operator with a positive weight. And well, a similar situation happens for free Banach lattices. Every lattice homomorphism between free Banach lattices will be of the form, will be a composition operator. And actually the symbol phi, which I wrote there, is going to be a map between the dual of the underlying Banach spaces satisfying certain properties. Okay, I'm not going to enter into the discussion of these properties, but these follow from the definition of the space and the norm and so on. Okay, well, so, but this is so far what we know. So we don't have yet, and it's probably false that, I mean, I would, maybe that's a bit naive at this moment, but I would conjecture that the answer to the previous question is negative, that one could give examples of non-isomorphic Banach spaces whose free Banach lattices are lattice isomorphic. But nevertheless, what we can do is transfer Banach space properties to Banach lattice properties and vice versa, okay? So for the next couple of slides, I'm going to mention some cases of Banach space properties which have an analog, a Banach lattice analog, via this correspondence from a Banach space to its free Banach lattice. And I took the liberty to write this as a meta theorem. This is maybe a personal joke with my colleague Mitchell Taylor. So we hope at some point we could prove something very general, but at the moment we have just instances of this kind of results. So I'm going to show you a couple of results in this direction. So I'm going to write always in blue the Banach space property of the underlying Banach space, and in red the Banach lattice property of the corresponding free Banach lattice. So the easiest or the first thing one can check is that being finite dimensional for a Banach space, it's equivalent to its free space to have to its free Banach lattice to have a strong unit. This is very much related to my previous comment about identifying it with a space of continuous functions, of course. You may complain being finite dimensional is not a Banach space property per se, it's basically an algebraic property. But okay, let's go one step further. Being separable, this is clearly a Banach space property, right? Because it involves both the vector space structure and the norm. And this actually happens, the underlying Banach space is separable precisely when the free Banach lattice generated by E has a quasi-interior point. Okay, and one could also go further and look at different ways of generating a Banach space. So for instance, one can look at weakly compactly generated Banach spaces, and it's very easy to check that if you start with a weakly compactly generated Banach space, the corresponding free space is weakly compactly generated as a lattice. This is related to a certain question. Oh, thank you, Amal. I'll try to keep with the time. So this is related to a question by Joe Distel about the coincidence of being weakly compactly generated as a Banach space and as a lattice, which we actually could solve with the technology of free Banach lattices. Okay, and another thing I want to mention is containing copies of L1. So if you start with a Banach space, which contains a complemented subspace isomorphic to little L1, okay, which is clearly a Banach space property, this happens to be equivalent to the corresponding free Banach lattice to have what we call a lattice complemented sublattice isomorphic to little L1. Meaning by lattice complemented, I mean, well, I have a sublattice, which is little L1, and there's a lattice projection onto it. And actually, this is also equivalent to, that should be in red too. This is also a Banach lattice property. This is equivalent to the free Banach lattice to contain a lattice complemented sublattice isomorphic to the free Banach lattice of L1. And I'm not having time for the, I was a bit naive. I was hoping I would have time to sketch the proof at least. But well, maybe if at the end I have time, I can comment on that. Okay, so I want to illustrate one more example of this correspondence. For that, I need to recall what is upper P estimates of a Banach lattice, right? We say that a Banach lattice satisfies upper P estimates, where P is just some number lying between 1 and infinity, when every time you take a finite collection of pairwise disjoint vectors, xk, when you sum the vectors and you take the norm, this is bounded above by the LP sum of the norms of the individual vectors. And you have a universal constant there, which is not depending on your choice of vectors or the number of them. Right, so this notion is related to convexity, as you know, and type and cotype and so on. There's another notion I need to recall. Again, if you're familiar to the theory of absolutely summing linear operators on Banach spaces, there's the concept of Q1 summing operator, which is a linear operator between Banach spaces, which maps weakly summable sequences to strongly Q summable sequences. And well, in other words, that you have an estimate like the one I have written here. So every time you take vectors xk, finite collections of vectors xk, you have a certain constant, which I call with this strange symbol, certain constant which is independent of your vectors and the number of them, which satisfy this inequality. Okay, so this is again, this is a Banach space property, clearly. It is somehow related to cotype of the space, okay? Yeah, well, I will skip further clarifications of this. So let me just show you our result. If you start with a Banach space E, so you take P and Q Hurler conjugate exponents, then one can characterize when the free Banach lattice over E satisfies an upper P estimate by looking at the identity on the dual, on the Banach space dual of E, and checking whether this is Q1 summing, right? With P and Q, as I said, conjugate exponents. So in particular, this property here, the identity is Q1 summing. This is very closely related to E star having cotype Q for Q for Q different from 2, I think it's, or at least in the case of Banach lattices. So, which is related to E having type P, right? So type is just a Banach space notion, and on the other hand, the free Banach lattice generated by that will satisfy an upper P estimate precisely when this holds. And okay, I think my time is over, so let me just thank you for your attention.
Thank you, Pedro, for this beautiful presentation. I'm sorry for the time. So, is there any questions?
Excuse me, I have a question.
Yes, Joseph, please go ahead.
Hello, Pedro. Hello, Pedro.
Hello.
Excuse me, if I understood your talk, means by free Banach lattice is the smallest Banach lattice which respect to this extension property. This is my first. If it is true, via false, yeah, I don't know. My second question is what's about free, not Banach lattice, but if the space is only normed, there is not stricter of Banach. There exists or not the free lattice for a normed vector space. And thank you.
So, okay, I think I understood the. So there were two questions. The first thing, yes. So if you start, so actually the free Banach lattice generated by a Banach space can be seen as taking the free vector lattice generated by that space and then taking the maximal norm on it. So in a way, it is, as you said, is the smallest thing you can think with that property. So it is because the norm is maximal, so the space is in a way minimal. So that I think justifies your first comment. The second question was whether you can do the same thing starting with a normed space instead of a Banach space. Is that right?
Yes.
Yes. So what you probably get is the same thing. I mean, probably you can define the free Banach lattice generated by a normed space, and what you end up is with the same thing as taking the completion of that normed space first. I haven't thought much about that, but I would guess that you would get something like that. If you don't use completeness also on the level of the Banach, so you could also try to do something like the free free normed, free normed vector lattice and generated by a normed space. But I mean, you could define that, but I'm not sure that would be very different from our construction. That should be, I mean, that's probably something to do there and to clarify, but I haven't thought about this.
Thank you. Thank you.
I think that Professor Azozi has a question.
Yes.
Hello, Pedro.
Hello, Youssef.
I have two questions. General question. When trying to show your results, you use the universal property more much, or the expression of the norm?
Yes, I mean, the universal property is much more convenient. It is easier to use, I would say. The norm, in a way, I didn't mention this, but the norm I gave you, in a way, is carrying the info. Of course, it carries the information for everything, but the norm arises from the universal property just by looking at operators into L1 spaces. So, okay. So if you just look at operators into L1 spaces, being able to extend them makes your norm to look something like this. So actually what we proved in our theorem is that knowing that you can extend to any L1 space allows you to extend to anywhere, to any Banach lattice, okay? But dealing with the norm, it is, I mean, at least it's an explicit norm. So you can deal with it, but it's not always easy to prove things about the norm. If you have some natural operator from a Banach space into a Banach lattice, then it is much more natural, or at least easier, to work with the universal property directly. But they are equivalent. So
I mean that are you forced sometimes to use the norm, not?
Well, that depends. Of course, that depends on the kind of questions you want to look at. Of course, for instance, there was this question about in the original paper by De Pachter and Wickstead, where they studied the free Banach lattice generated by a set. There were a bunch of questions about the norm of the free Banach lattice, and of course, these were very hard to deal with because they didn't have an explicit expression of the norm. So they were asking whether the norm had the Nakano property, Fatou property or Nakano property. And we could answer these questions, but only because we had an explicit expression of the norm. For many other things, you're right, you can just play with the universal property. But if you want to know specific things about the norm, then of course you need that. Is that your question?
Yes. Also, I want to ask, is Banach lattice algebra also considered for free?
We haven't considered this. No. I think maybe Marcel had something to say. Marcel Dejeu, maybe he has something to say about that.
Yeah, thank you for a very nice talk, Pedro. Yeah, there's a kind of general procedure to create free objects with norms. You can take a free vector lattice over a Banach space and then introduce the norm in an abstract fashion, and then you get the free Banach lattice. You don't get this very nice expression for the norm, but you can easily show existence of the free object, and this beautiful formula for the norm is then the actual theory. And you can use a similar approach for, say, free Banach lattice algebras over sets or over vector spaces or whatever. You first create a free object in an algebraic category, and then you can introduce the norm by exploiting the universal property that you want the analytic object to have. And there's a paper of mine that will appear in the Proceedings of Positivity 10 in I think in July or something, where this is explained. There are a great number of free algebraic objects, so to speak, in ordered categories are constructed. They're shown that these exist. And to each of these, you could apply this general machinery to introduce a norm on these algebraic objects, and then you get the free object in an analytic category. So the existence of these objects is can be established rather easily from the general procedure, and then the actual inner structure of it is the challenge to analyze.
Okay, is your paper published already, or
about this free what I just mentioned? Yeah, I can send it to you.
Yes, but the question is also to Pedro for the paper with Tyler.
Oh, sorry. Which paper? No, the one I'm speaking about. It is still work in progress.
I'm sorry. Oh. But we need to move to the next presentation. Sorry. It's time.
Yeah, so
I have a question, please. I have a question.
I'm sorry, but time is up. You can write the question in the discussion.
Okay, not problem.
Thank you.
Okay, no problem.
So I can say goodbye to all of you and see you soon. I hope this.